So going on to this slide then, as you can see on the left-hand side at the top there, those are the issues that I was discussing, the limitations of traditional production lines that Masterly is attempting to address. And below that, you can see a set of objectives that we've targeted, which is to, I won't go into these in great detail because largely these are technology based and the purpose of today is to focus on the social science. But obviously you can see objective 3 is to develop user-friendly interfaces for robotics machines, control and programming. But as I will explain as we go through, the human-centered or user-friendly approach crosses other aspects of the project more widely. So just to go through our use cases in Masterly, we have the Kleeman elevator control electrical cabinets assembly use case that you introduced, Marta, earlier on. So the current state is obviously a very highly manual operation involving quite small scale assembly, and the vision is to move to a more collaborative system which would reduce the need for manual application of manual tasks that are unskilled, repetitive, not particularly healthy, not very enjoyable for the human operator to perform, thereby enabling them to focus more on the more skilled and cognitively satisfactory tasks. And we have some KPIs that are beyond the ones that I've listed there. I'm focusing very much on this in this presentation on the human-centered aspects. So we're aiming for reduction of manual tasks via the implementation of robotics by around 50% improvement, productivity in terms of cycle time reduction of a 40%, which isn't necessarily a human-centered approach, but it relates to the other issues below that, which is to focus on psychological impact and increasing worker acceptance of the new systems by 15%. And the cycle time reduction is also a key driver of improved ergonomics by reducing task time and musculoskeletal risk. So reducing the amount of time that the operator is engaged in posturally or physically demanding strenuous activities that are not very conducive to well-being. Moving on to the decathlon sportswear logistics and packaging use case, we have the current state where manual operators walk through large areas of a warehouse and pick orders, individual orders for packaging and sending out to customers. And the Masterly vision is to automate this as far as possible. Reducing manual strain like the Kleeman case, and to focus on improving the human enjoyment of the task, allowing them to focus more on the quality control and skilled aspects of the task, and removing the physical manual handling strain. And again, we have a productivity and performance target of about 80% improvement by reducing the manual tasks using automation, in reducing cycle time reduction, increasing, in this case, worker satisfaction as well as acceptance, and by, again, the 15% reduced musculoskeletal risk target. And then finally, I do apologise. Oh no, that's right. So the Aeronova task, use case task, is currently a task that involves quite heavy manual handling, moving large components in aeronautics around, and our target is to implement a human-robot system, which actually is not as collaborative as the other two use cases, because the aim here is to replace that heavy manual handling and the risk of injury and collision that it involves, focusing on allowing the human to conduct the smaller assembly tasks, the more cognitively skilled tasks, and take away that dangerous heavy lifting. And again, there you can see some human-centered KPIs, and the description of the improvements that we're trying to achieve there, very similar to the other ones. So moving on to what we are doing in terms of the human-centered analysis. In work package 1, it's worth mentioning we engaged in some user-centered requirements capture. And then in work package 4, we focus on user-centered design of interfaces. And for that, we have adopted a 3-stage or 3-spoke methodology. One aspect of the methodology is to really focus on understanding what the human currently does. We believe that it's very important to, before doing any design and implementation work, to understand what the tacit skills involved in operations are. We can look at standard operating procedures and work standards to understand what the system designers intended people to do, but we know that people don't tend to stick to those very rigidly. In many cases, there's often deviations from standard operating procedures. For good reason. We know that operators tend to adapt things because they want to make it better, easier for them for personal reasons. Maybe it could be their physiology or their natural abilities, or it could be that they find a better way than was originally designed. So we want to understand that, and we use eye tracking for that, where we get operators to perform their tasks wearing the eye trackers, which gives us operators' own perspective of the task being executed. It gives us a good combined field of view, horizontal and vertical view. And we have these systems that involve, the eye tracker systems that involve accelerators, gyroscopes and magnetometers, I can't say it, which accurately track their eye gaze and compensate for head movement. So we get a very accurate video recording, but also a microphone recording the verbal communications, which gives us additional detail. Excuse me. This gives us some various outputs, including those examples that I put there in the small pictures. Some heat maps, which show us how much people look at certain areas. So it shows us the intensity of where specific parts of the field of vision are concentrated on. That's important because it shows us what grabs people's attention, and therefore this could indicate, it could be explained by areas of the work naturally, but if we ignore that, we can also look at how that might infer that these are areas of problems and issues, for example, where they might need to really focus on something to get it right, or because there's some confusion. We also look at dwell times in that middle picture there. That's an example of where we can see how people have looked at things for a length of time. Again, that may indicate where there's a problem because there's extensive decision making needed, some confusion, etc. And we can also look at scan paths, which is the order, the sequence, if you like, in which different areas of a field of vision are looked at. And that indicates what gets people's attention first, or cues to action, what they then need to do next, and so forth. And these are really good indicators of the current manual task, how it's being performed. They tell us where those problem issues are, and that then can advise us on where we may need to design out problem areas, where a robot would actually be more beneficial because it could be designed to take away some of those problem areas, or where the actual manual process itself in the human-robot interaction needs to be redesigned. So this analysis shows us the areas of the task and environment that demand greater attention, decision-making, that are prone to error or difficulty, or those that are effective cues to aid awareness. And we find that eye tracking not only gives us that objective output, we can also use that recording for playback to the operators if we want them to tell us how they do things. And so because a lot of what they do is so based on tacit skills and non-technical skills, they're not always aware of that procedure. It's like we always use the example of driving your car to work. There's a lot of aspects of that journey that you wouldn't be able to tell us if we asked you to tell us about it, because it comes naturally. But if you recorded it, you would be able to then explain, well, this is the indicator for when I turn right. This is, you'd be able to then recall more about that, the decisions you made and the task process you undertook. Excuse me. So the second part of our work package for user-centered analysis was to conduct hierarchical task analysis, and that's based on the eye tracking videos. Hierarchical task analysis deconstructs manual processes into individual component steps at various depths of scrutiny that suit the analysis, and it helps us reveal deviations from standard operating procedures. It helps us identify those decision-making points. Helps indicate the process change potentials where there may be, again, we identify those problem areas and where we might need to design those out when we redesign a process to use a robot. We also use task decomposition, which is an extra layer. It extends the HTA by providing another layer of analysis that classifies steps into things like cues, decisions, actions. And so we can identify the steps that utilize tacit knowledge and skill. And that's important because tacit knowledge is often the part of a human operation that shouldn't be maybe transferred to robotics. It's that sort of skill and creativity that only a human can bring. And it helps us highlight error points and then identify remedial actions that we can integrate into the redesign of the process. This analysis shows us the specific steps of the tasks that are problematic, that helps us to engage in user-centered design and more effective function allocation. The third part of our user-centered analysis is the application of psychometrics. So we use psychometrics, as you all know, to capture current levels of psychological states, indicating potential areas of concern in the current processes. And also this provides us with this quantitative baseline data set against which we can measure impact in future assessments. So gathering a baseline of how people are responding to the original manual process means that later on when we implement our solutions, we can then measure again and we can assess the differences. And so we can hopefully, it's improvement, measure those impacts and assess whether we're achieving those KPI targets that I mentioned earlier. We use various psychometric tests. We tend to use reliable and valid assessment tools that are already available because they have proven validity and reliability levels. And so three key ones that are used in Masterly here are the physical discomfort scale, because we want to assess the difference in ergonomic, postural, physical differences between the as-is manual task and the to-be one after we've implemented solutions. We measure mental workload because we know that's very, very important to how people, how satisfactory a new system is. And we are not targeting blanket reduction in mental workload at all. We measure 6 dimensions of current mental workload using the NASA TLX, and we use that because we know there are optimal ranges of mental workload. We don't want to go for too little workload because we know that then is unsatisfactory, and we don't want to overload people. So we need to get that optimal range. And we also measure situation awareness, which we also know is very important for automated systems. People need to understand what's happening at any given time. So we want to ensure that we also achieve an optimal level of awareness in relation to task characteristics. And this analysis overall allows us to understand the physical and psychological impacts of the project solutions and quantify them. So those three together allow us to understand the user-centered design of interface, to improve it, to understand what needs to be allocated to a robot better.